Earth. So that's the other reason why you have the really large concentrators. But the low temperatures, you don't. The biggest problem with a window, besides the pressure issue, is temperature. You can't shove too much light through a standard window on Earth without it breaking, because of just, you don't aim a normal telescope at the sun because it will shatter the optics. So it's the same principle here. Well, on Mars, it's so much cooler to begin with, and you can use that to your advantage, so that you can cool the optics down even if you do have a smaller aperture that you're using. So again, you would have essentially a mirrored entryway here, because you are being very sloppy with the ability to get light in there. Going forward, next slide. Okay. I already walked through this. There is one good point here, though, that I missed earlier, is that if you had this same thing on the Moon or Mercury, because their axial tilt is almost straight up and down, that 46-degree arc is now a 3-degree arc. So you have a much narrower mirror if you did the same thing on the Moon or on Mercury. And I've already walked through most of the rest of those points. So next slide. Again, the side view stretched out. Next slide. And a little bit more detail of the villa architecture and so forth relative to this whole thing. Food production, that size design would roughly feed 2 people indefinitely. So if you had that, and then you had your husband and wife couple or whatever behind it, and whatever, you could have that. What you would do as an actual colony is you would have at least 2 or 3 additional units. And you would dehydrate food for longer term storage, because you can dehydrate food, maintain most of the nutritional content for about 20 to 30 years, depending on what you're running with. And it also takes up considerably less volume. And of course, all you then need is water to bring it back. The other advantage of this is that you can then use that same food for return flights to Earth that has been made recently, as opposed to something that was made 5-10 years ago and exposed to radiation in deep space much of that time. This is one of those weird little things about, we actually have exactly the same problem that the early explorers of America had. Their food that they carried on the ships in 400, 500 years ago had a relatively short shelf life. So when they came to America, if you read like the diaries of the Cabot expedition, first thing they did is they went into the forest and harvested timbers to rebuild the ships, and they planted a garden, and then they explored down the coast. And then when it came to be the end of summer, they hopped back up the coast, got to that garden, harvested it so they would have fresh food for the return journey to Europe. It's the same principle here. You would have, when you expose dehydrated food to deep space, you tend to have radiation deterioration, not of the food so much, but as the nutritional content. So you could boost the nutritional content by making it indigenously and have very high nutritional content for a return voyage that you wouldn't have if you had brought it from Earth, stored it, and then brought it back. So biosphere design, briefly. I already went through why we wouldn't use ducks and chickens so much, but we would tend to focus on tilapia. Dead fish are obviously much easier to find when they're dead. They tend to float, as opposed to a chicken, which is going to hide somewhere and not going to be, not going to be a good thing. The nice thing about fish is they tend to stay where you put them. The other thing about it, and if they don't, they've got other issues, but they're not going to escape into the ecosystem. The only negative with tilapia is they need to be at a very high temperature relative to other fish. They need to be at least 65 degrees. So that becomes an issue in terms of having something that warm on the surface of Mars. Next slide. Tilapia and duckweed they're both good protein sources. Tilapia eat duckweed, and both are used in water filtration systems because it's basically a carp, which tends to eat anything, and a algae, plant sort of thing that has it's very simple structure. It's its own family. It's a very good protein source not only for the tilapia but for ducks or for humans that can actually pre-process. So you have an all-win situation here in terms of that whole thing. It tends to make the environment cleaner as much as it does dirtier. The warmth is the only real negative. And they're very hardy. They're considered an invasive species in Florida. But because they need to be at such a high temperature, it's the only place where they can be an invasive species in the United States. Next slide. Ground plants, you tend to plant, this is back to the permaculture thing, you tend to plant legumes and so forth as nitrogen fixers to go from the atmosphere into the plant zone, and then you have other plants that exploit that later on. We can keep going. Pollination is a real issue. This is going to seriously narrow your selection of plants in the early missions, because unless you can figure out a way to get bees there or something like that, you're going to be very limited in terms of the flowering plants. This may be something where you have so few plants or so few trees, you would do it by hand with a Q-tip or robotically. Have some sort of robot arm that reaches around and does this sort of thing until you can actually get bees or something along those lines into that environment. Just a quick thing though, a bumblebee that can barely hover on Earth, if it had the same thrust to weight ratio on Mars, because of the lower gravity, would shoot through the ceiling like a rocket. So you'd have to work something out there. Next slide. Lots of alcohol in the honey, I don't know. Anyway, mulch is, again, it's sort of a passive system. Again, fish is an excellent fertilizer. You've got a good closed loop there. Next slide. And air management, if you have too much carbon dioxide, you're on freaking Mars. The atmosphere can be compressed and brought back in. If you have too much oxygen, convert it to ozone and use it for sanitation. Next slide. Water management, again, you can use ozone as a treatment thing. The ozone breaks down in about 45 minutes, so now you've got highly oxygenated water that's no longer toxic to the plants and animals. And you've got the ability to use that in a way to take care of the bacterial population. Next slide. Compost management, you might bring in something other than tilapia, like worms and other sort of things, to break down the mineral, the plant life. Next slide. Prototype demo flight. This would be a very small demo thing that would hopefully be small enough to fit through an airlock. There's a lot of advantages to putting this on an early HAB prototype flight where you don't have a crew, but you want something living, so you have something that could go there in a HAB or an ERV and be basically take up the space that the crew would otherwise have taken up. So next slide. It would be relatively simple. You'd probably just use fiber optic light pipes from a collector on the outside that would be more active, and then you'd also have LEDs to subsidize the light during darker seasons. You have an extremely simple system, a robotic system that would monitor, it would essentially garden, it would chop and drop and harvest things, and gather samples. You would have a simple system for compost processing, another simple system for atmospheric control, water processing in the same methods I mentioned, and any kind of in situ analysis for storage for either a return capsule on an ERV or a pickup by a future crew. So those are the high points of the talk. And these are just more points about that. Theoretically, if that garden existed on Mars on an early prototype mission and the crew found it, they could transfer that module to the next HAB and the next HAB and keep the HABs going and just do an end-of-life study on how that thing would work until they could actually build a colony to put those things in. So you would have maybe greater than the 3-year or 6-year or 9-year span. Even if the first HAB that originally arrived in had died or had shut down, you could probably have moved it to another HAB if it's small enough. And that's pretty much the gist of the talk. And we've got 2 minutes for questions left. So.
Any questions? Yes. Do you consider absolutely necessary to protect crops against radiation? I thought it was discussed matter.
It's rarely discussed because normally you think of things in a relatively short life cycle. When you talk about stretching things out for a long period of time, like talking about trees and so forth, then you have a greater radiation exposure. Even then, it's not as biologically complicated. It's got thicker cell walls. It doesn't have to worry about, ruining its hypothalamus because it doesn't have one, things like that. So do you need all that radiation protection? No. But the crew is going to spend an awful lot of time in that. So,
for the crew, I understand, but for the crops?
For the crops, you need some, but not as much, not nearly as much.
Because also the pressure level for greenhouse is much lower than for main. So is it effective to have both together?
You can compromise this a great deal. This is shoving everything as far to one side of the table as possible. just to show that it can be done, and there's a lot of benefits to doing that. Because exactly the same chamber for a crew versus a garden, then you could have a crew/garden. You can make one that's just twice as long and have both in the same zone, and have a completely passive, theoretically, system that may not need life support at all, just monitoring. And
one more question.
okay.
Sorry.
Yes, you were. Yeah.
Would you maintain a higher CO2 level in there for plant growth? Would it help if it were higher than, say, what was in crew cars?
Yes, to a degree. It would also. It's just a question of what do the plants want, and I think that you would have to determine that optimized for the exact environment. It would depend on which plants you selected, and obviously we're nowhere near having that solved. Other than the tilapia, duckweed is a good combo for a very simple system like in the early experiments. So, once you've selected your plants, they would select what CO2 level they prefer.
Okay. Thank you very much, Ken.
Thank you.